how the application of OLS is not, will not provide reliable results when we are using time series analysis or when we are using time series data. So I have shared with you people the data file, which is basically a file having the name is time series 1.xls. This file is having four variables. LM3 is the log of money supply, that is LM3. Okay. LIIP is natural log of IIP series. LCMR is natural log of call money rate, which is an indicator of interest rate. LER is log of exchange rate. Okay. Let me tell you, many times we say that index का log नहीं लेना चाहिए. We shouldn't take a log of any index. So even that we can do. We can consider IIP without any index, or without taking log. Sorry. Here a log has been taken. Let me tell you, this data is starting from 1991 month 04. That is April. Okay. So we have to first of all open this time series in Gretl. Then we'll be using this time series analysis. Let us open Gretl. Are you doing analysis with me? अपना कैमरा ऑन कर लो बच्चों सारे. You can switch on your camera, please. All of you. Yeah. All of you, please switch on your camera. Right. Now open Gretl. In Gretl, what we are going to do, we are going to open the data file. Go to open data. Explore your file, as my file is available on desktop. Example files. Here I will be clicking .xlsx time series 1. That is my data file which I am going to open. Click open. I have to start import at first column and first row. Click OK. Now, Gretl is asking whether means the imported data is interpreted as undated data, cross-sectional data. Do you want to give the data a time series or panel interpretation? I click yes. Because it is a time series data, click here, time series, forward. Now, there are different types of time series frequency. Annual series, quarterly series, monthly, weekly, daily 5 days, daily 6 days, daily hourly, and so on. See, many times in share market, hourly data is available. So daily data is available. You can choose means the type of frequency as per your requirement. Since our data is a monthly data, I am using this monthly option. Click forward. So my data is starting from 1991. To change the date here, 1991 month 04. Okay, as I told you, I have already told you this data is starting from April 1991. So I have changed the date to 1991 month 04. So up to last date, that is 2014 month 09 September. So this data is from 1991 04 to 2014 month 9. Let me tell you, we have only given the beginning date. The end date has been suggested automatically by the Gretl. Click apply. End date has been suggested on the basis of your length of the time series. So much this data is open. Actually, there were different detection of different problems like heteroscedasticity, multicollinearity, autocorrelation. So today I'm going to tell you people the detection of autocorrelation with the help of this time series data. So then we will be finishing unit 1. Go to model. If I use ordinary least square, suppose I have to estimate a model where I want to see whether my suppose this Suppose LM3 I am taking as the indicator of money supply, money demand, because MD is equal to MS in equilibrium. So suppose LM3 has been taken as indicator of what you say demand for money, and I am estimating LM3 as a function of say LIIP output. Okay, then LCMR, that is the rate of interest, and LER, that is the exchange rate. In an open economy, obviously, exchange rate matters a lot in determining demand for money. LIIP is affecting LM demand for money because classical says output affects the demand for money. Keynes says demand for money is affected by interest rates, so interest elasticity has been computed. Since I have taken the log, ultimately I am affecting, I am estimating monetarist type of demand for money function, where MD is say we generally write it as Py raised to power alpha and R raised to power beta. Okay, this type of function taking log of both sides, we say log MD is equal to log P plus alpha log Y plus beta log R. Okay, this function I am going to estimate. So ultimately, exchange rate I am also taking as let e raised to power phi, the psi, and small e raised to power ut, all are basically time series. Uh, so log of yt, log of rt plus psi log of exchange rate plus ut. This regression function I am estimating, where yt's proxy is in IIP, that is index of industrial production. The proxy of RT is the call money rate. Proxy of exchange rate has already been given as exchange rate. So log of exchange rate has been taken. So this type of function I am going to estimate. Alpha is the output elasticity of output elasticity of demand for money. Beta is interest elasticity of demand for money. This psi is the exchange rate elasticity of demand for money. But this function I am going to estimate. P is the obviously general price level. Now, if I estimate this function using OLS, obviously I will go to model ordinary least square. LM3 will be my independent variable. The independent variables will be output proxy, that is LIIP, interest rate proxy, that is LCMR, is log of call money rate, and LER, log of exchange rate. Click OK. Now, once you click OK, we can see that output is significantly affecting, exchange rate is significantly affecting the demand for money. Interest rate is not affecting significantly the demand for money. No, the issue is, are these coefficients reliable enough or not? In time series analysis, we see if we go by the goodness statistics, we say R square is very high. That is 98.48% variation is explained by these three variables in demand for money, right? F statistics is highly significant. See, the F statistics and p value is zero. But issue is the Durbin-Watson statistics. You can see this Durbin-Watson statistics is 0.845931. So 0.845931 means what? There exists autocorrelation in this model estimation. Hope you people know the Durbin-Watson statistics represents the existence of autocorrelation. If I write this as yes. No, this Durbin-Watson statistics is showing autocorrelation. How this autocorrelation can be represented in the Durbin-Watson framework? I show you. We generally say when someone is asking, but how to observe this autocorrelation in these models? If I show you, hope you know the relationship between autocorrelation and Durbin-Watson statistics. Do you know the relationship? Which is Durbin-Watson statistics or D statistics is summation Et minus 1 whole square upon summation Et square. Do you remember? पता है ना कि नहीं? This is
Yes,
Durbin-Watson
sir.
statistics. Okay, if I open square, so can I write it as summation A square plus B square minus 2AB? Right? So can I write it as summation Et square upon summation Et square plus summation Et minus 1 square upon summation Et square minus 2 summation Et minus 1 upon summation Et square लिख सकता हूँ.
Yes, sir.
Okay. Now for very large samples or for large sample, summation Et minus 1 square is equal to summation Et square. Okay. Because they are the proxy of variance, and variance is assumed to be constant because of the assumption of absence of heteroscedasticity. Variance is assumed to be constant. So once variance is assumed to be constant, and variance is assumed to be constant, summation Et minus 1 square is equal to summation Et square. So can I treat both of these as equal? Can I write D is equal to, this would be unity, this would also be unity, 1 plus 1, 2, minus 2 summation Et minus 1 upon summation Et square लिख सकता हूँ. क्या नहीं? So 2 is common. 2 is common. 1 minus this formula. That's a summation Et minus 1 upon summation Et square is nothing but the formula of autocorrelation coefficient, that is rho cap. So Durbin-Watson is equal to 2 into 1 minus rho cap. Okay, which implies that D is equal to 2 into 1 minus rho cap. Okay, if there is no autocorrelation, that is rho cap is equal to 0, then Durbin-Watson must be is equal to, without 1 minus 0, 1, 2 into 1, 2. Okay, so Durbin-Watson near to represent no autocorrelation. As Durbin-Watson falls, it means autocorrelation rises. It means autocorrelation rises, right? If autocorrelation is perfect, okay, then 1 minus 1, we can say if rho cap is equal to unity, then What would be D?
Zero.
0. If rho cap is equal to -1, then what would be Durbin-Watson?
So 4.
4. Okay.
4.
So, बच्चों, this is the case. This is the case. So, as Durbin-Watson will become near 0, as it will be falling, we will say that the autocorrelation rises. As it goes near 2, we say the autocorrelation is falling. Okay, so you can observe that this value 0.8459. Will you substitute 0.8459 in this formula? 0.8459. D is 0.8459. So 0.8459 is equal to 2 into 1 minus rho cap. Okay, so 1 minus rho cap is equal to 0.8459 divided by 2. Okay, so rho cap is equal to 1 minus 0.8459 divided by 2. देखो कितना आता है बच्चे? What would be the autocorrelation coefficient? Tell me. फोन हो गया आपके पास? कैलकुलेट करिए. What would be the value?
Sir, it will be 0.5755.
0.5755. So high autocorrelation is there, isn't it? 0.57 positive high autocorrelation is there. The positive high autocorrelation exists. So we have detected the autocorrelation today in OLS estimation. When we are estimating, we are using OLS on time series data. So बच्चे, the issue with the application of OLS is that in case of time series analysis, whenever autocorrelation is present, your R square is very high and Durbin-Watson is very low. Okay. So when R square is very high, Durbin-Watson statistics is very low, we can say that there exists the problem of autocorrelation. And whenever there exists the problem of autocorrelation, the simple OLS estimation of the model is not applicable. We have to go with either time series modeling. We have to ultimately go with the time series modeling. Then we have to see whether we need to go with the univariate models or multivariate models. In any case, you are applying this, what we say, if you are estimating a multivariate model with OLS, it means you have to go ahead with the multivariate time series analysis. So when multivariate time series analysis, you have to talk about this co-integration analysis. You can't simply go ahead with the OLS estimation. OLS estimation is neither reliable nor dependable. You can't means we can say that these estimates are spurious estimates. The estimates they look good, but they ultimately their practical applicability, the reliability is zero. Okay, so this is the problem of autocorrelation. This problem of spurious regression. Though coefficients look statistically significant, they look very high, they look very significant, fit seems to be good, but ultimately fit is not good. So that was about unit 1. From tomorrow onwards we will be starting with the unit 3, that is the time series analysis. Unit 2, I have already told you that I am skipping for time being. I will be starting that unit after finishing unit 4. Okay, at the last we will be taking up unit 2. Do you have any question in this estimation?